In the previous videos, we've been looking at independent demand and how we manage inventory with independent demand. We looked at economic order quantity that goes with a fixed order quantity. We looked at fixed order interval and our order up to level and our order interval amount. And then we looked at the single period model. How do you know how much to order when the good that you're ordering goes bad? Well, now I want to look at dependent demand. Dependent demand is where we have lumpy demand. That is, our demand depends on demand for something else. So we have sub-assemblies, something that we're making that then gets used to make something else. And as we look at dependent demand, we have to look at how much for each of those sub-assemblies. And how much we make is going to depend on the demand for the final product. So we're going to have to look at how do we figure out when to make those sub-assemblies and how much to make. When it comes to dependent demand, there are two types of systems. There's a push system and a pull system. So a push system is when a batch of items is made and pushed to the next work center. So as soon as it's done, it gets pushed on to the next location. So if we're making vehicles, for example, maybe one part of our plant is making the chassis and another part is fabricating the plastics for the dashboard and things like that. So if it's a push system, then our department is going to make those chassis and assemble them. And then as soon as we're done, we're shipping them over to another department where dashboards and things get added to that chassis. Okay. A pull system, in comparison, is when a work center pulls the items from that previous workstation just as it's needed. So if I am doing assembly on the vehicles, instead of waiting for a big batch of chassis to arrive and start working, what happens is we do our work and we pull the chassis in when we need to start doing that part of the assembly. We pull in the plastics for the dashboards just when we need to put them onto that unit we're assembling. So we can have a push system, push it when it's done, or pull it when we need it. So if we have a push system for our dependent demand, then we are using material requirement planning. Material requirement planning is where you determine the purchase and production of dependent demand components. So we need to figure out how much of those sub-assemblies to make, what materials we need to make them, when we need to do it, so that we can push it on to the next part of the process. So what we're going to look at in this video is how material requirement planning works. In a pull system, where you pull the inventory just when you need it, that is a just-in-time delivery system. And we have videos you can check out on how just-in-time manufacturing works. But let's focus in this video on material requirement planning. All right, let's talk first. Let's create a bit of a blank page here. I don't know where to put it. There we go. All right, so if we are doing material requirement planning, okay, which we said is a push system, then we need to first talk about the objectives. What are we trying to accomplish with material requirement planning? So first, we want to ensure the availability of materials. So we want to make sure if we're making that truck that that plastic for the dashboard is going to be available when we need it. So we need to ensure the availability of materials. And part of that means we're going to have to do a good job forecasting demand for the finished car so that we can make all the sub-assemblies, the components we need in it to make sure we have what we need available. We do want to maintain the lowest possible inventory. So both the push and the pull system, both just-in-time and material requirement planning, would like to have the lowest possible inventory levels. Now, having low inventory levels is much more successful in a pull just-in-time system than it is in a push material requirement planning system. And we're going to talk about why that is later in this video. Just-in-time manufacturing focuses on lean manufacturing and focuses on eliminating waste and not using inventory to disguise defective product or quality issues. So really focusing on quality management to help reduce that amount of inventory even further. So check out the videos on that. So our objectives, we need to ensure the availability of materials, maintain the lowest possible inventory, and our material requirement planning, we're going to plan our manufacturing activities. When are we going to make what? When are we going to have delivery? So schedule deliveries. And when are we going to place orders for our materials? So purchasing activities. If you need nuts and bolts to attach that plastic dashboard to the vehicle, when do you need those nuts and bolts? When do you need the piece of plastic? Okay, so how much do we need to order and when do we need to place that order? When it comes to material requirement planning, there are a number of inputs, things we're going to need to help us do this planning. The first is what is called a master production schedule. So to give you an example of what a master production schedule looks like, okay, a master production schedule looks like this yellow here at the top. We forecast our demand, we figure out how much inventory we already have on hand, and how much we're going to need to produce and when. So the master production schedule is going to be our anticipated build schedule stating which end items, so that final product, the car, okay, so which end items are to be produced when, and in what quantities. And then we work backward through that master production schedule. So we forecast the demand for that final product, and then that's going to tell us how much we're going to need of the final product, which tells us how much we're going to need of the sub-assemblies, and when we need to start on those sub-assemblies, and when we need to place the orders for the pieces that go into those sub-assemblies. So we're going to look at a master production schedule later in this video. But in terms of inputs, we need a master production schedule, an MPS. We're also going to need some other items. We're going to need what is called a bill of material. A bill of material says here are the components in our final product. So what do we need to make it? So for example, if I'm making a chair, then my bill of material says I need 2 side rails, a crossbar, a back support, I need a seat, the leg assembly part, so sub-assemblies, leg, back, and what's in each one of them. So the leg assembly has 2 legs and a crossbar, So we're breaking down everything we need to make our product. All right, so it's going to be a listing of all the components. So that's your raw materials, your sub-assemblies, all your parts needed to produce one item. So what do I need to make one chair? I need the pieces that make the back assembly, which include side rails, crossbars, and the back support. I need the pieces that make up the leg assembly, the legs, the crossbar, so I need all those pieces. With that bill of materials, we also want to include a product structure tree. The product structure tree shows how that bill of materials, those different parts, how they then make up the final product. So it's a diagram like you see here at the bottom that says a chair has these different sub-assemblies, the back, the leg, the seat, and then it breaks it down further and said the leg assembly includes these components. The back assembly includes these components. So it's helping us understand not only the inventory that we're going to need, but how it's related and how it's going to make the components that make up our final product. Okay, so we're going to need our master production schedule, so that's telling us about timing and forecasted demand. We're going to need our bill of materials, so what's in the final product. Our product structure tree, how can we group it together into sub-assemblies, and then we're going to need some inventory records. That is, how much of these parts do we already have on hand? Are some of these parts scheduled to arrive in the near future? We're going to add this information to our master production schedule. All right, so once we have the bill of materials, the product structure tree, and our inventory records, we can start to flesh out the master production schedule. So let's look at how we would do that. All right, so we need to forecast demand. We call this forecasted demand for our final product the gross requirement. So this is demand for an item during a specific time period. So let's assume that we have forecasted that in week 11, we're going to need 100 units. Okay. Then we need to look at, do we have any scheduled receipts? So scheduled receipts are open order scheduled to arrive. So they're coming from some other vendor where you've outsourced production or we're buying it from a supplier, and it's scheduled to arrive from a vendor at the beginning of a period. Okay. So are we scheduled to have, let's say 30 units were going to arrive at the beginning of week 4? Okay. Well, the projected on hand, that's the amount. So that's the amount of inventory we already have. So inventory expected to be on hand. Nothing like defining a term with the same term. But this is the amount that we already have on hand. So if, for example, we start week 1 with 10 units on hand, already in storage. Then in week 2, we still have 10 on hand. And in week 3, we have 10 on hand. In week 4, we have the 10 on hand plus the 30 that arrive, which means in week 5, we now have 40 on hand. Okay, so this would continue with our 40 on hand until we had our forecasted demand. So remember, we need to meet the requirement of 100 units at week 11. Well, if we need 100 units and we have 40 on hand, then our net requirement, which is your gross requirement minus your projected, minus your scheduled receipts, this is how much we're going to need to make. Okay? Now, we also can add to this some safety stock, so we can have some extra just in case. Now, in this example you see here, they had gross requirements of 100 and net requirements of 120. If there's no projected on hand and no scheduled receipts, then they're adding 20 safety stock to their gross requirement, just in case to have on hand. If we were to say, okay, there is, let's say, okay, so if we have a gross requirement of 100, we have on hand 40, then we're going to need 60. So our net requirement, we could make that 60, or we could make it 60 plus a bit to allow for some safety stock, right? It's an extra just in case. So let's have no safety stock and change this 120 to say 60, okay? Now, we need to make 60. So then we look at what's called planned order receipt. Planned order receipt is the quantity that you plan to receive. Okay. So if we need to have 100 units for our customers on week 11, we have 40 on hand right now. Our net requirement is 60 unless we want to add some safety stock to it, which means that the quantity that we need to receive finished product, we need other parts of our factory to send us 60 completed units so we can ship them out on week 11. So our planned order receipt would be 60. Now, that 60 doesn't have to match the net requirements. It won't match the net requirements if you have to order in batches. So if we can order exactly how much we need, then our net requirements and planned order receipts will match 60 and 60. But if we have to order in batches, then our planned order receipt isn't necessarily exactly the amount we need. For example, if we have to order in batches of 100, then what that means is in week 12, we're going to have the 40 that we had on hand, that goes out the door to meet the customer's requirements, and 60 adds to that for the 100, but that means we're going to have 40 left on hand in week 12, that extra from ordering in batches. So we could order exactly what we need. That's what we call lot for lot sizing. In which case the net requirement and planned order receipt would be the same number. If we have to order in batches, then the planned order receipt is going to be in increments of your batch. So in that case, maybe you're using fixed order quantity. So you're always going to be ordering the same amount. And so that could be a different number. Then we have planned order releases. Planned order release is our planned order receipt plus our lead time. So if it's going to take 2 days to move that material from other part of the department, or 2 weeks to get it all moved, then what we're doing is we're taking our planned order receipt and we're shifting it over 2 weeks' time. Okay, so planned order release is going to be a time shift from the planned order receipt for the lead time. How long is it going to take from when you place the order to when it arrives? That lead time can include lead time to simply move the product, or it can include lead time as well because what you're ordering doesn't get made until that point, and so then you have to add that as well. Well, if we have a subassembly A, then the gross requirements for subassembly A, because they're a part of the final product, depend on the demand for the final product. So if we needed 100 units of the final product, then our gross requirements for assembly A is going to depend on that. Let's bring that back. If you need 2 of A to go in every one of your final product, then your gross requirement is going to be 2 times that planned order release, and so our gross requirement here would be 200. Notice that they align, the planned order release and the gross requirement, because essentially here what's happening is subassembly A finishes product A on week 9 and then ships it over to the final assembly area, 2 weeks time to do that, and so final product assembly area calls subassembly A on week 9, says, hey, send it over, and it takes 2 weeks to move it all, and then it's ready for the customer on week 11. So you should have vertical alignment here. And if you only need one of the subassembly in the final product, then the numbers are going to match. If you need multiple amounts of subassembly A, then you're going to multiply it times that. Now, in this example, there are scheduled receipts in week 5. We're expecting 40 units of subassembly A to arrive. We have 0 on hand, so at week 6, we now have 40 on hand. And that 40 carries us all the way to week 9. So if we have a gross requirement of 200 and 40 already on hand, then our net requirement is going to be the difference between that. Okay, 200 minus 40, so 160. If you decide to have, if you decide to have safety stock, then that number might go up a bit. I don't know why all my numbers keep disappearing. All right. So this becomes 160 here. And if our net requirements are 160, we're going to need to create 160 of subassembly A. If we can do lot for lot sizing, then the planned order receipt is also 160. And here now we take into consideration the lead time. So in this case, it looks like that is 1, 2, 3, 4 weeks. And so our planned order release is 160 in week 5. So planned order release and planned order receipts are always going to be the same number. It is simply showing the time shift that comes with the lead time. Net requirements and planned order receipts can be the same number if you have lot for lot sizing. You order exactly what you need. If you're ordering in batches, then your net requirements and planned order receipts will not be the same. The gross requirement, subtracting the scheduled receipts and projected on hand, will give you your net requirements, unless you're going to add some safety stock to that as well, in which case the net requirement will be slightly more than the gross requirements minus the scheduled receipts and the projected on hand. So in terms of overall process, in terms of material requirement planning, when you are building your master production schedule, the first thing you have to do is establish your gross requirements. What is that forecasted demand? Then you need to determine your net requirements. And of course, net requirements comes from taking your gross requirements minus how much you have on hand minus the scheduled receipts as well. All right, once you determine your net requirements, then you're either going to use lot for lot sizing, oops, or batch to determine your planned order receipt. Then you're going to time phase those requirements to determine the planned order release. When do you need to make the order to make sure you have enough so that it can go in the sub-assembly, so it can go in the final product, so it can meet the forecasted customer demand. Now, when we are doing material requirement planning, there are some challenges with this method. So let's just create one more new page here. So challenges. Challenges with MRP. Okay. So challenges with MRP. Well, the first is that it expects lead time to be constant. Okay. We're expecting that between when we place an order and when the order arrives, it's always the same. And this isn't true if you order more. So the challenge with MRP is we expect the lead time to be constant regardless of the amount of work. So if you order 5 units or you order 10,000 units, we're assuming that lead time is the same, and that's not always realistic. So because of that, we often build in safety time, extra time just in case. So in our example, here we had 2 weeks between planned order release and planned order receipt. If that lead time, if we're concerned that it's not going to be enough, we might shift this planned order release even earlier in time to add some safety time, a bit of a buffer, just in case our order takes longer than we expect. So you can see the system starts to get a bit bloated as we start to add in safety time. Well, there's also a tendency within material requirement planning to add in safety stock. What if you don't have a good forecasted demand? What if your demand is more than expected because you work this back in time to figure out when all the sub-assemblies are? If you didn't forecast accurately, you can't meet the customer demand. So we tend to kind of just pad the system with safety stock, extras just in case. So material requirement planning can become bloated with safety time and safety stock as a buffer just in case. So there is, let's see, pressure to increase lead time just in case. Okay. Well, if you increase your lead times just in case, then we get more work in process inventory. MRP assumes infinite capacity. So if we go back to our MPS here, well, what if the gross requirements weren't 100? What if instead they were 500? Well, in terms of the setup, it would be the exact same process, we would just change the numbers. So it really assumes infinite capacity. That is, we could just make more if there was more forecasted demand. We could make 5 times as much without changing the amount of time things take or the amount of materials that we would need. We would just 5 times as much, same amount of time. And so material requirement planning is falling more out of favor in industry because of that assumption that if you wanted to make twice as much, you could do it in your existing with the same number of workers and the same amount of time. And that's really not realistic. And to protect your company from the fact that you might need more, we tend to pad everything. More safety time, more safety stock, and then we start to get bloated, which is why the just-in-time management became so popular and dominates inventory management now for dependent demand, is because it's really about reducing that bloat, not building in all that safety stock, reducing the amount of excess inventory that you're holding on hand. So if we go back to our list here of challenges, we expect lead time to be constant regardless of the amount of work. There's a pressure to increase the lead time, add some safety time. We're assuming infinite capacity, that you can just make twice as much in the same amount of time. And the key here is that any kind of small change in your master production schedule result in large changes. Because it's working backwards, any tiny change gets that ripple effect all the way back to all the sub-assemblies and all the parts within the sub-assemblies. So small changes in the material, small changes in the master production schedule result in large changes in those planned order releases. So if we're looking back here at our table, we could see the ripple effect. If we decide to change, like I did, the number, so I said, okay, let's have some scheduled receipts and add some projected on hand, and you start to see all the numbers change. Well, if we add safety stock, those numbers would change as well. If we decided to add in some safety time, so that instead of a 2-week period here, we made it 4, then everything below it, subassembly A and all the other components related to it, all get shifted. So little tiny changes have a huge ripple effect in material requirement planning. So we look at material requirement planning to understand how a push system works, but also to help us understand some of the downsides or challenges with inventory management. Do you add extra time? Do you add extra safety stock? What happens if you do? And to understand how just-in-time management has become popular because it addresses some of the bloat or problems created in material requirement planning.